All right, so I decided to grade questions 4B, the direct and indirect proofs. And mostly these went well. So question 4B is the following. Given P implies not Q, not R implies Q, and P, we want to conclude, what do we want to conclude? We want to conclude R. So that's our goal. So the first thing, which I noted in an announcement when I posted this, is to make sure you understand what this theorem is saying. This theorem is saying you have three hypotheses and a conclusion. And so a direct proof can work a few different ways, but if you just kind of look at your hypotheses, right, there's a P implies not Q. If you put those together, you can chain them and get to not Q really quickly. And here's something which says not R implies Q, while indirect reasoning says if Q is false, then not R must be false. So you can put together a direct proof a number of ways. So here's a direct proof. 1, P implies not Q. That's a hypothesis. 2, I'm just going to go ahead and do P. That's a hypothesis. And then 3, I'm going to put those together and say not Q. That's direct reasoning of 1 and 2. And then I want to use this middle property here, this middle hypothesis. I need to state it. It has to be part of my proof. Not R implies Q. That's a hypothesis. And if I don't like indirect reasoning, I can take the contrapositive of this and say not Q implies R. That's the contrapositive of 4. And now I can do direct reasoning. I can put this together with 3 and say R must be true. That's direct reasoning of 3 and 5. Or like I say, you could simply state this and then put that together with 3 and say indirect reasoning says R must be true. And technically the contrapositive of statement 4 is not Q implies not R. I snuck a double negation in here and simplified it to R. I'm okay with that. Replacing a not R with R, you can do that in one step. But if you wanted to be totally formal about it, technically this says since not R implies Q, not Q implies not R. And then you'd have to put another statement that says not Q implies R because of double negation. But, you know, that's one of the things that if you want to slip it into one step, I'll let you get away with that. Okay, once we've written down Q, that is what we were asked to demonstrate. That's where we can say QED. If we want an indirect proof, we're going to start off by assuming the negation of the conclusion, and then try to find a contradiction. Well, if we write down not R, here's something we know, not R implies Q. Let's put that down and do some direct reasoning. So not R implies Q. That's a hypothesis. Put those together, we get Q. That's direct reasoning of 1 and 2. Well, we also know that P implies not Q and P is true. So we can repeat the first 3 steps that we had in our direct proof. We can say P implies not Q. That's a hypothesis. And P, that's a hypothesis. And we can combine those with direct reasoning and say not Q. And that's direct reasoning on 4 and 5. And now we have a contradiction between 3 and 6, because we've shown Q and we've also shown not Q. Therefore, R must have been true, because if we negate R, we get a contradiction. So R must be true, and that's what we were asked to solve. So that's where our QED goes. All right, so almost everybody got the idea of the proof down perfectly, okay? The steps were sound, the reasoning was sound. Let me talk about the things that you want to watch out for when you're doing these. First thing is, make sure you list the full reason. Don't just say not Q because of 1 and 3, of 1 and 2. Tell me how 1 and 2 go together. They go together with direct reasoning or detachment. Okay, make sure you list the reason. Don't just say contrapositive. What is it the contrapositive of? It's a contrapositive of 4. Okay, make sure you list that. So number each of your propositions, and when you use two propositions to get in a new proposition, name those propositions. Okay, so that's one thing. When you write down something like not Q, what we're saying is that this proposition is true. Not Q is true. When we write down P, what we're saying is P is true. So a few people wrote down things like step 2, they would have written P is equivalent to true. That's redundant, okay? Simply by writing P, we're saying P is equivalent to true, okay? Technically, we could put an equivalent to true after every statement we write. That's really the essence of a proof. We're writing true statements. But we don't usually say is equivalent to T. We just write the statements. The understanding is anything we write is true. It's equivalent to T. So you don't want to explicitly say that, though, because it just makes the proof more complex looking. You can't say things like at this point, you couldn't say, so let's say you come down this far, right? So you don't want to say something like 3, 4, and 5 are a contradiction, right? It's true, 3, 4, and 5 together leads you to a contradiction. But you can't immediately look at this and see 3, 4, and 5. Well, we've got Q and P, which are different propositions. We've got a conditional proposition. Why is that a contradiction? Well, because if you take P and you take P implies not Q and you put them together with direct reasoning, you get not Q and not Q contradicts Q. That's worth putting a little more in your proof, okay? You never want to ask the person reading your proof to have to think too deeply, okay? So spell it out. Put those together with direct reasoning to get not Q, and then say not Q and Q is a contradiction. That's pretty easy for somebody to believe. Oh, you said Q is true, you said Q is false. Yeah, that's a contradiction. Okay? So always finish your proof, and the biggest thing I saw was people didn't quite finish their proof. They had all the steps, and I was confident you could finish the proof, but you got to finish it through all the way to the end, and really just kind of like drive it home to whoever's reading it. That you know, this is clear. Okay, the other thing which I see occasionally, but I'm seeing it a lot right now. Let's look at the direct proof. So statement 1 was P implies not Q. That's a hypothesis. Statement 2 is P. That's a hypothesis. Okay, I would make statement 3, if you're going to combine those, not Q, direct reasoning. Here's what some people are writing. P implies not Q, and P implies not Q. And what you're doing is you're really writing down a formal definition of direct reasoning or detachment. Okay? This is always true, regardless of what P and Q are. It has nothing to do with the truth of P or the truth of this implication. This is always true. Okay? This is not the same thing as writing down not Q, though. If you're going to use not Q at some point, you've still got to write down not Q. And the reason for that is direct reasoning of 1 and 2. This is not actually part of your proof. This is the definition of what I'm calling direct reasoning, using statements 1 and 2, right? But we don't tell the definition of direct reasoning as part of our proof. We assume the person reading this knows what direct reasoning or contrapositive or conjunctive simplification, they know what those things are. We list them as reasons. Okay, so this is extra stuff, and it's not complete enough. You still need to say not Q is a true statement, right? And this doesn't say not Q is true. This says, given this, and this, and this, I can write down not Q. So you combine 1, 2, and 3, right? So I saw that in several submissions, and I just crossed out this and put a circle around that, right? All right, does that make sense? Okay, so so that was it for the logic. So other notes on homework. I'm going to write these down, and I'm going to take off for them next time, but I didn't this time. So full name. Believe it or not, there are other people with the same initials. First name and last name, please spell them out full unless you're like officially going by an initial, in which case we'll figure out something. Header on top of homework. So your staple in the corner, your name, the date, the assignment, the class, the page, number out of number, and so on and so forth, right? Take a look at the homework submission guidelines, make sure that's on there. 8.5 by 11, I'm still getting about 20% of the assignments on like 8 by 10 paper. And I end up missing some. So 8.5 by 11 paper, if at all possible. Do the problems in order. Yeah?
So, for example, the one that had do direct reasoning and then the indirect reasoning, would you want those ordered like A1, A2, or do you want them like all as one of them?
I was sort of thinking of like A direct, A indirect, B direct, B indirect, C direct, C indirect. But that one, if you did them like ABC direct and ABC indirect, I'd probably like take mercy on you, because it's not totally clear. But what you don't want to do is like, you know, do question 4, do question 6, do questions from 3.5, do questions from 3.8, and then, oh yeah, and here's 4B, right, from that first set. So just keep them in order in some reasonable way. Clean edges, almost everybody's got that, right, if you rip it out of a spiral notebook. Yeah, you had a question earlier too. Yeah. Yeah, just because. I think on the Discord channel, if you go back to last quarter in the beginning of the term, somebody posted a template that you could print out in Word that had, you know, just fill in the blanks. Some people like using that. It's kind of nice. All right, I think that's all I had for comments on homework. So any questions on any of the other homework questions? Yeah. Which chapter, which section?
8.8, 4B.
3.8, 4B. Let's see what we got. All right, 3.84. The universe is the set of all people, and M of xy is a proposition that x is the mother of y. And then part B says write a statement using quantifiers and m to say that everybody has a grandmother. So m of xy m of xy is the proposition that x is the mother of y. So how would you describe in just plain spoken language that somebody has a grandmother, that a particular person has a grandmother? So let's say y has a, well, how do we say y has a mother? Using quantifiers and this proposition m.
For all y, there exists an x, like that every child is the mother, is that the distinction?
Okay, so for a particular y, right, just y is some person, how do we say that y has a mother?
That could be with x and xy.
Right, there exists a person x such that x is the mother of y. That means that y has a mother. How would we say that x has a mother? And let's not reuse y. It's exactly the same thing, right? There exists a z, or let's say a g, such that g is the mother of x. Well, let me change my variables here. Let's show that a person P has a mother. I'm going to say there exists an M such that M is the mother of that person. And to show that M has a mother, I'm going to say there exists a person G such that G is the mother of M. And to show that a person P has a grandmother, we need to show that they have a mother and that that mother has a grandmother. Right? So we can write this a few different ways. We could say there exists a G, comma, M such that G is the mother of M and M is the mother of the person. Or there exists a G such that let's see, can I do this another way? There exists a G such that there exists an M such that G is the mother of M. Yeah, I'll just write it as a conjunction. Yeah. M of, and a big M in here. The idea of that is great. The implementation is problematic because X and Y are supposed to be people. They're elements in the universe, and this is not a people or an element of the universe. This is a proposition. So we're saying that a proposition is the mother, or this is the mother of a proposition, right? The spirit of it is right, but mathematically it doesn't work out. So show that the person has a mother and that that mother also has a mother, right? That gives the first person a grandmother. Anybody else have any other ways of doing that? All right, other questions? All right, so I think your midterm is Friday, is that correct? Does anybody know? Is it? Oh, that would be nice. 222 is on Friday, and I was like, how could I schedule these on the same day? Oh, you got plenty of time. February 12th. All right, that's a week from Wednesday. We don't have to worry about that. All right, but we are in week 5 now, out of a 10-week term. So like, end of this week is the halfway point, which is crazy, because it feels like it just started. So here's the heart and soul of this course. Induction. If a stranger comes up to you and offers you $1 million if you can answer a question, you don't know the answer, say mathematical induction. There's a good chance you'll be correct. Particularly if that person happens to be me.
Are you offering $1 million?
I am not.
Mathematical induction.
There you go. All right. This is really the big takeaway from this course. And to understand and talk about mathematical induction, we need to understand propositional logic and proofs and things like that. So we've been working on those. And we're going to use a little bit of set theory in what we're doing. And we'll use some other things that we'll come back to again and again. And I'm going to call this actually induction and recursion. And starting in about a week in CSE 222, we're going to start looking at things that involve a technique called recursion. It's a programming concept, and it's really funky, and it's powerful, and it's usually pretty confusing. But we're leading into recursion and recursive programming through this pathway of mathematical induction. And so this will fuse nicely with where we're going next in 222 when we talk about binary trees and other things. So let me give an example. Suppose I say, can you walk to New York? That's where I grew up. Can you walk from here to New York?
Yeah.
How do you know? Have you ever done it?
No.
Okay, how do you know that you could do it?
Because there's. Huh? Oh, yeah. Well, because there's solid ground.
Because there's solid ground, okay, I'll grant you that. And
Oh, yeah.
you have legs, and what do legs let you do?
Walk.
Walk, what does that mean? Do they let you walk 3,000 miles?
Eventually.
Eventually, but we don't know that. We haven't proven that because we've never walked 3,000 miles, right?
You probably got through your whole life.
Probably across your whole life, yeah.
Oh, here's an idea. So because, like, America started on the East Coast and we got all the way out here, then that means that we had to walk from the East Coast to here, which means that we can walk from the West Coast to there.
Except we might have taken a wagon or something.
Did you say you could take a step, you can always take another step?
Yeah, so we could say, right, we know that we can walk one step, right? If we've done that before, we can say, okay, if I'm standing in one particular spot, I can move 1 foot in a given direction, right, as long as there's ground there, right? And if you can move 1 foot in that direction, guess what? You can move 2 feet in that direction. How? Move 1 foot and then move 1 foot again. Well, if you've proven that you can move 2 feet towards New York, you can move 3 feet towards New York. Do whatever you have to do to get 2 feet down the road, and then just go 1 foot more. So here's what we can do in terms of a proof. Given if you are at location N, you can get to location N plus 1. We can just use this proposition, which is true, multiple times. If you're at location N and you want to get to location N plus 10, well, apply this proposition to say, hey, if you're at location N, you can get to N plus 1. And if you're at N plus 1, you can get to N plus 2. And if you're at N plus 2, you can get to N plus 3. And after you write 10 lines of that proof, you've proven that if you're at location N, you can get to location N plus 10. And if you want to get to New York, which is location N plus, I don't know, it's like 1.5 million or something. I don't know how many feet it is. 5,280 times 3,000. 15 million. So if you want to prove that you get to location N plus 15 million, you just need 15 million lines of a proof. Right? It's easy. Get a really big sheet of paper and a fine point pen, and you can do it. But you also need to know something else. You also have to be given that you can get to location N. Because what we can do after 15 million lines of proof is prove that if you're at location N, you can get to location N plus 3,000 miles. Right? If you combine that with the fact that you can get to location N, then you can prove that you can get to location N plus 3,000 miles. That's New York City. Okay, if you're given this, and I say, can you prove that you can walk to Paris? Well, you can do the same thing. If you can get to, Germany, to the border of Germany, right, you can get 1 foot beyond the border of Germany, and if you can get to 1 foot beyond, you can get 2 feet beyond, and so on and so forth. But do you have a way to get to the border of Germany? Right? Well, you can't walk to the border of Germany from here because there's water in the way. So you need both of these things. You need to know that, if you're at a certain spot, you can get 1 spot further, but you also need to know that you can get to a starting point. Okay, so this is just the journey of 1,000 miles thing, right? This works with ladders. If there was a ladder that was, infinitely tall or unlimited tall, right, could you use that to climb to the moon? Well, assuming that if you're on a certain rung of a ladder, you can go up 1 more rung, right? All you got to know is that you can get to the first rung of the ladder, and you can get to the nth rung of the ladder for any n, including the rung that's 250,000 miles up in the air, which is where you step off onto the moon. So you need both of these steps. This is mathematical induction. This is what every mathematical induction proof is going to come down to. You're given 2 things. Right? You're given that you can move from a step n to a step n plus 1, and you're given that you can get to a starting point. If you know that's true, you can put these together and say, I can get to any n that I want. Okay, that's the essence of every proof we're going to write for the next week. The challenge is usually showing this. Usually showing you can get to some location n, that's pretty easy. The challenge is showing that if you can get to n, you can get 1 step further. All right, got the basics set up. It's really short to write, but it's a huge set of concepts. So let me write this more formally. I'll do it down here, but we'll rewrite this frequently. So let P of n be a family of propositions. and I'm just going to say n is bigger than or equal to 0. It doesn't really matter where we start. Usually it's bigger than or equal to 0 or bigger than or equal to 1, but we could start anywhere. So we can prove P of n for all n bigger than or equal to 0 as follows. Okay, this is a powerful statement. This says this proposition is always true. It's true for n equals 0, 1, 2, 10, 50, 5,000, 10 million, and 6. Right? This is saying P of n is true for all n bigger than or equal to 0. Wow, that's a lot of n's. That's a lot of propositions that we're saying are true. How do we possibly prove that? We could prove them individually, but there's an infinite number of them we would have to prove. And you know, proving P of 5 is probably pretty easy, because P of 5 will say some specific thing, and these specific things are usually not that hard to prove. The problem is we don't want to prove an infinite number of them one at a time. So we have a technique called mathematical induction, which lets us prove P of n is true for all n bigger than 0 by only proving two things. So we can prove this as follows. 1, prove P is true for n equals 0. And then prove that if P is true for n, then it's also true for n plus 1. And I'm guaranteeing to you that if you can prove these two things, 1 and 2, you have proven this circled thing. You've proven P of n for all n. So let me write this slightly differently. And this thing I'm about to write, this is called mathematical induction. Mathematical induction says the following. Given P of 0, given P of n implies P of n plus 1. For all n bigger than or equal to 0, we can conclude P of n for all n bigger than or equal to 0. So let's think about this. P of 0 is straightforward. That's just one proposition. So let's compare the second line with the conclusion. This second line, we have to prove it for an infinite number of n, right, for all n bigger than or equal to 0. But we get to assume that P is true for n, and we only have to follow from that a proof that P is true for n plus 1. That's a lot easier than actually proving P of n is true for all n. Because you're going to get to assume that P is true for n, and then just show it's true for the next value of its whatever its variable is, right? This is just a little step. This is the big whopper. This is P is true for everything, okay? But if we can prove that it's just true for this little incremental step, we can put that together with P of 0, and we're done. Okay, and this is called the base case. This P of 0. And this next piece we want to prove, that's called the inductive step. So every proof by mathematical induction involves a base case and an inductive step.
The inductive step is that entire second row.
It's this entire second row. try an example of this. I'm going to keep this as my statement of mathematical induction. All right, let's play a game. We are going to picture a floor which is tiled. Anybody ever grow up with a tiled floor? You like, depending on where it is, you end up staring at it and looking for patterns, right? And you find a pattern and you wonder if it repeats, and it's like, is there, ever this particular pattern or something like that? So let's picture a tiled floor. And all of these tiles are going to kind of be the same. It's sort of a boring tiled floor. And let's say we want to retile it. Okay, and we go to Costco and they have a really good deal on this huge box of tiles, right? Dirt cheap, but they're all kind of funny shaped. They're all shaped like a letter L. And so we know that we can take these tiles and we can put them down on our floor and we can turn them around and put them together in such a way that we can try to cover most of this floor, right? For example, if I take one of these L-shaped pieces and I put another L-shaped piece right next to it, I can get a nice little 2x4 region, 2x3 region that's like rectangular shaped. And I could take those and I could spread them out. And if my room was 20 by 30 tiles, I could cover my floor perfectly, right? So we want to know, if we buy this box of L-shaped tiles, can we use it to cover the floor of our kitchen? And our room is perfectly square-shaped, except there's one spot we don't want to cover because there's a pipe coming out of it. And maybe that pipe is right here. Maybe it's somewhere else. Okay, here's a theorem. Suppose that your room is set up such that it's perfectly square and each side is a power of 2 in length. So it's 8 by 8 or 16 by 16 or 1024 by 1024. And let's say that exactly one of these tiles has a pipe coming through it and you don't want to cover that tile, but you want to cover everything else with these L-shaped tiles. There is a theorem which says you can do that. It's guaranteed. There's a way to tile a 2 to the n by 2 to the n room with one missing spot with these L-shaped tiles. You're not allowed to cut the tiles, by the way. You're not allowed to have any hanging over the end. You're not allowed to have anything that's not covered, and you're not allowed to overlap them. It's got to be a good, honest tiling. Okay, and you can do it as long as your room is 2 to the n by 2 to the n and you got one square missing. And we can prove this using mathematical induction. Let's make a proposition. Let P of n be the proposition. You can tile a 2 to the n by 2 to the n room with one missing square. Using L-shaped tiles. Propositions don't have to be mathematical. Well, we got 2 to the n's in there, but they can talk about, we'll talk about postage stamps, we'll talk about unicorns, we'll talk about all kinds of propositions in here. So P of n is the proposition that you can tile a 2 to the n by 2 to the n room using L-shaped tiles. And this only makes sense if n is bigger than or equal to 0. If n is equal to 0, what's 2 to the n? What's 2 to the 0? right? So if n is 0, this proposition says if you have a 1-by-1 room with one missing square, you can tile it using L-shaped tiles. Well, if it's only a 1-by-1 room and there's one tile you don't want to cover, you don't have to do any work, right? You've kind of covered it in the vacuous sense. But if you prefer, you could start with n equals 1. That's a 2-by-2 room, right? And the goal is if there's one square missing, can we tile that? So let's start off with n bigger than or equal to 1. Yeah.
So, I think I have a misunderstanding as to what the L is.
Okay.
So is it like a Tetris L where there's like 3 and 2?
It's 1, 1, 1.
1, 1, 1.
So it's symmetric. Okay, our goal is to prove P of n for all n bigger than or equal to 1. That's what we want to do in the next 5 to 10 minutes. And you could start trying to do this. You could get a 16 by 16 room and come up with a tiling and do a 32 by 32, right? But we want to prove it for all n. Right, so a 4 billion by 4 billion room we can cover with a bunch of these L-shaped tiles perfectly. Okay, well, if we want to use mathematical induction, we need to do the following. We need to prove our base case. We're going to prove P of 1, and then prove P of n implies P of n plus 1 for all n bigger than or equal to 1, and we'll conclude P of n for all n bigger than or equal to 1. So we need to prove a base case. Well, what does P of 1 say? P of 1 says you can tile any 2 to the 1 by 2 to the 1, that's a 2 by 2 room, with one missing square. Well, how do we prove that? We prove that by doing it. So here's a 2 by 2 room, and let's suppose that this square is missing. Can I tile that with L-shaped pieces? Yep. I can put my L-shaped piece down right here, and I'm done. You do what?
Pictures and proofs?
Yeah. So what if this square is missing? Not a problem. Drop my L-shaped piece here. And you got 2 more cases. And if you can convince the reader that those are the only 4 possible scenarios, you have shown that this proposition is true for each of those cases. You've proven that P of 1 is true. This is a good question that Travis just asked, though. Can you draw pictures and proofs? So in the 70s, right, there was this thing called the 4-color map theorem. Anybody ever hear of this? So it's this theorem that if you have a map drawn on a piece of paper and you try to color in the countries on it so that, you know, no 2 countries are the same color, all you need is 4 colors. That's always sufficient. And it hadn't been proven when I heard about this, and it was such an easy problem to understand that I started going crazy drawing pictures of weird-shaped countries and trying to color them in, right? And you would just number the colors 1, 2, 3, 4, and I was so sure I was going to find, you know, a counterexample to this this idea. And somebody eventually proved that 4 colors was always sufficient, and the proof was basically to reduce all possible maps to, I think it was one of several hundred different models, and then color each of them with 4 colors or fewer, and that concluded the proof. But this proof involved computer work. It was a computer that determined, you know, this set of maps that you could choose from and then colored each of them, and it was kind of controversial. It was one of the first times that somebody proposed a mathematical proof that was in large part computer program output. And people weren't sure for a while whether this actually constituted a proof or not. And we do this all the time now. But, you know, in the 70s, it was kind of like a little bit strange. So, I mean, it's a excellent question, like, are we allowed to draw pictures in proofs? And we could come up with an elaborate system for describing tilings of floors using these L-shaped pieces and probably, you know, make this very rigid. But we're not going to be that rigid for this, right? As long as it's a reasonable proof. Now, if you draw a piece of graph paper and put in some L's and say you can just generalize this and it'll always work, right? It's got to be more rigid than that. I used to study an area called algebraic geometry, and around the 1900s, a bunch of Italian mathematicians were just forging ahead in the field of algebraic geometry, coming up with all these great results, right? And everybody was building on these results, and it was sometime later that people discovered that some of their proofs weren't quite true. They were relying a lot on intuition, and it worked for a while. They were coming up with things that, you know, were in fact true, but eventually it got to the point where there were theorems being proven that weren't actually proven and turned out to not be theorems at all. They turned out to be false in some cases. But whole branches of mathematics were built on top of this Italian school of algebraic geometry, which then, you know, slingshotted to a very rigid school, I think in the 30s, that sort of restructured the whole field. All right, so we're going to use pictures because it's a Friday in 4 days, so that's a good reason. All right, so we can prove P of 1 like this, right? This is what P of 1 says, and there's, you know, the only possible places that we could have a hole in a 2x2 floor, and we can tile it in each case. So I'm going to say P of 1 is true. Okay, but we got to prove this inductive step. We got to prove that if this is true for n, then it's true for n plus 1. Once we have that and we put it together with P of 1, then we can say P of n is true for all n bigger than or equal to 1. But we got to prove this inductive step. Okay, and this is kind of fun. Given P of n, prove P of n plus 1. That's all we got to do now. Okay, so consider a 2 to the n plus 1 by 2 to the n plus 1 room. I'm going to split this room into 4 quarters. And I'm going to note that each of these quarters is 2 to the n by 2 to the n. Now one of these quarters is missing a tile somewhere. Okay, let's suppose that there's a tile down here in this lower right quadrant that we do not want to cover. Question, can we tile the remainder of this quadrant using L-shaped tiles? How do we know?
We assume that.
Because we're given P of n, right? P of n says a 2 to the n by 2 to the n room with one missing tile can be covered. So because of P of n, this can be covered. That can be tiled because P of n is true. Now that doesn't work for this quadrant because we're not missing a tile. Do you have a question?
I think so. Let me find the words to ask it.
Okay. So this quadrant, P of n doesn't apply because it's not missing a tile. Same with this one, same with this one. But this one that happens to be the quadrant with a missing tile, we can totally cover that. That's what P of n says. Well, yeah,
Okay. So, are we still assuming that n is greater than or equal to 0?
let's do 1.
1?
Yeah.
Okay. So if that's the case, and we know and we have proven t to the n,
Mm-hmm.
can't we just prove that, like, n plus 1 is also, like, greater than or equal to 1?
We haven't proven that P is true for n bigger than or equal to 1.
Oh,
So far, all we've proven is P of 1, right? And we're in the process of proving that if it's true for n, it's true for n plus 1.
yeah.
Once we have both of those, then we can show that P of n is true for all n bigger than or equal to 1.
Gotcha.
This is what we're trying to get to.
Right. And so I guess because that bottom right
Mhm.
square, that's a very small tile.
This is one tile missing in the middle.
Right. But isn't that tile on its own not like P of 1?
That's technically, well, P of 1 is a proposition,
Right.
right? P of 1 is the proposition that a 2x2 room with a missing tile can be covered with L-shaped pieces.
Yeah.
So what's your question again?
So I guess because it's a 2 to the n,
Mm-hmm.
but we proved like that 2 to the 1 was the proof that we did, right?
Mm-hmm.
And so if we still haven't proven that 2 to the n works, right?
We're assuming 2 to the n works,
We're assuming that. Okay.
and we're trying to prove 2 to the n plus 1 works.
Gotcha.
Okay. We haven't proven that 2 to the n works, right? Mathematical induction, we prove P of a base case, and then we prove if it works for n, it works for n plus 1. We're not proving it, we're not saying it works for n. We're saying if it works for n, it works for n plus 1. That's the inductive step we're trying to show. But that, together with the base case, together with this magic wand we call mathematical induction, then lets us say P is true for all n. All right. So, we've proven that we can tile the lower right quadrant. We could tile each of these if they were also missing a square, right? We could still use P of n. So here's what I'm going to do. I'm going to take out a tile over here, and a tile over here, and a tile over here. And now, I can tile all the rest of this, except that little missing corner, because I know P is true for n. I'm assuming P is true for n. And I can tile all of this upper left quadrant, except for that little missing corner, because that's a 2 to the n by 2 to the n with a missing piece. P of n says I can tile that. And I can tile this upper right quadrant, except for that lower left corner, because of P of n. So I've got my whole floor tiled, except the one piece that I want to skip, and this little L-shaped corner piece. And I drop one more tile right into that little corner, and my whole floor is tiled.
If you wanted to prove it mathematically, like, not even mathematical induction, but like with numbers, you just use a modulo, right? It's like 2 to the n times 2 to the n minus 1. We're given that that modulo, that 3 is equal to 0. You just add 1 to that and show that.
Well, you need more than just one more than a multiple of 3, right? You need to know that you can actually fit these pieces together in a way that they fill in the space. Say again?
So it wouldn't work if you just use modulos.
That might be part of it, but that's not sufficient, I don't think.
Yeah, because that's assuming you could divide them up however you
Yeah,
want,
yeah.
adjacent to each other.
And if it's 2 to the n by 2 to the n plus 2, I don't know if you can tile it, but that's still one more than a multiple of 3. Or one more than a multiple of 4.
If it's 2 to the n,
There's other shapes of rooms that your argument would work on, but I'm not sure you can actually tile them. Right? You also need to somehow know whether these pieces overlap nicely or not. But this is a proof that if P of n is true, P of n plus 1 is true. Now, we made an assumption that our missing tile was down here. We need to do this 4 times. Because what if the missing tile is over here? Is your proof still going to work? Well, yeah. We'll cover that with P to the n. We'll take out the corner in these 3 regions, tile those with P to the N, and then drop an L-shaped piece like that. And then do the same thing if that's got the missing square and if that's got the missing square. So you need to do 4 cases, just like we did for our P of 1, but they're exactly the same proof, right? We can say without loss of generality, assume that we're missing a tile down here. Okay, that proves that P of N gives us P of N plus 1. Therefore, by mathematical induction, P of N for all N bigger than or equal to 1. So that lets us prove that we can always do this floor tiling. It also gives us an algorithm for tiling the floor. So you want to open a floor tiling business because you got all these L-shaped things from Costco, right? And everybody has 2 to the N by 2 to the N floors with one missing spot. So you want to open a business, and you know somebody has a 4 by 4 room that they want tiled. And let's say they're missing this square right here. Well, how do you do it? Well, tell them it's going to take 4 days to tile their floor. Split it in 4 pieces. Come in the first day and tile this section down here. Well, we'll just drop an L-shaped piece here. And then mentally block out these 3 spots. Come back the second day, tile that quadrant, come back the third day, tile that one, come back the fourth day, tile that one, and then on your way out the door, cover up those 3 corner pieces. Hey, there's a tiling of a 4 by 4. So just like Hilbert and his hotel, people are like, whoa, she's so good at tiling floors, I'm going to hire her. I have an 8 by 8 room. But I don't want you to take 8 days. I want you to do this in 1 afternoon. And let's suppose, I don't know, let's suppose that this is the spot they don't want covered. Well, break it into 4 by 4 regions. We have a solution for tiling a 4 by 4 room with a missing square, right? If it doesn't happen to be that missing square, we can repeat this process to find the solution for that, and we can tile that up with our solution. And then we just sort of mentally cut out these corners. Well, this is a 4 by 4 region with a missing square. We know how to do that. We just did that the day before, right? So repeat that process, tile that, do the same thing for here and here. So we have an algorithm for doing an 8 by 8 room. Can we do a 16 by 16 room? Heck yeah. How? Split it into 4 8 by 8s and use our 8 by 8 algorithm to tile the missing spot in the 3 other regions with the corners missing, and then drop down your tile in the end. And if you can do a 16 by 16, you can do a 32 by 32. It's just 4 16 by 16 puzzles, each of which is 4 8 by 8 puzzles, each of which is 4 4 by 4 puzzles, each of which is 4 2 by 2 puzzles, each of which we know how to do because we have our 4 base cases for doing a 2 by 2 room. Now let's say you don't want to have to keep track of all of this though. Somebody's got a 1024 by 1024 room. And first thing you're going to have to do is solve the 512 by 512 case. To do that, you have to solve 4 256 by 256 cases. And that's a pain, right? So here's a better way to do this. And this is what we're going to do in 222. So this is 1024 by 1024. And this is 512 by 512. And there's a missing square up here. And we're going to pop out these corners here. We're going to outsource. We're going to go to our friend who opened a 512 by 512 tiling business. So all they do is tile 512 by 512 rooms. And we're going to say, hey, here's the layout of the room. Can you give me a solution? And we'll give them the layout, and they'll give us back a solution. And then we'll say, okay, here's another 512 by 512 missing tile. Give me a solution to that. Here's another one. Here's the fourth one. Give me those 4 solutions. And give them $10. You get your 4 solutions. You use those to tile a room, and you charge $15. You just made $5. And another of your friends who does the 2048 by 2048 business, they get an order, and what do? They come to you with 4 of these floors and say, hey, I'm missing a tile from this. Can you give me a solution? You say, yeah. And you outsource, the 4 pieces to your friend and put them back together. That's a perfectly viable business model, not really, for tiling floors, okay? Terrible business model, but we can write code to do this as an algorithm. And the whole trick to writing a function called tile my floor with L-shaped pieces, and you tell it how big the dimensions are and where the missing piece is, the whole trick to making that work is you have to be able to call a similar function with a smaller floor size. And what's going to make this work in programming is that functions can call themselves. And you don't actually have any friends who are running the same business. It's really just you. Yeah. So when you say, okay, give me the solution to the 512, you walk out the front door, you put on a hat, you come in the back door, and you solve that problem, and you leave it there on the table, right? That's exactly what our programs are going to do, okay? Our functions are going to call themselves, and we can think of it as walk out the front door, come in the back. It's a totally new day. I'm a new person. Here's my problem. There's my solution, right?
That's a money laundering scheme.
Yeah. All right, so that's recursion in a nutshell, okay? We're going to rely on it heavily for once we're done with hashes. Everything else we do in 222 is going to be recursive. Everything we do in 223, everything you do at a university, is going to be doing recursion, right? Pretty much the rest of your life. But it's really just this model, okay? And it comes out of mathematical induction. And a good mathematical induction proof often comes along with an algorithm for free. We'll not only show that something is doable, but we'll end up with a way of doing it, which is kind of cool.
Is it true that to learn recursion, you first need to learn recursion?
That's what they say. The key to understanding recursion is to understand recursion. And recursion will feel like you're cheating. It will feel like you're not doing anything, right? I mean, what have we done in doing these floor tilings? The only time we ever actually tiled a floor was in these 4 cases. Right? That's really the only time we actually thought about how do we cover this floor, right? Everything else is just pass it on to somebody else and say, hey, cover this floor. And it's only the person who's got the 2x2 business who actually has to tell you how to place the tile. It's just putting it all together in the right way.
So, is there a way to take it a step further and show that all 4 of those are the same way? So you have to do even less work? Just by rotating?
Yes, so I mean you can do this without loss of generality, which can usually work, but it can get you into trouble sometimes. But if you look at this, it's pretty clear there's nothing magic about this upper left tile that I picked. If I pick the upper right tile, that's just taking this and rotating it. So yeah, you can do that. And usually the base case is pretty silly. It's really just kind of plug in and see that this is obviously true. But it's got to be done somehow.
And if you did it with memorization, you have to store the results somehow. Like, are we going to get into that at all? Dynamic programming?
Not in here, but in 222, yeah. We'll deal with problems that if you're not doing that, they are intractable. They just run forever.
Is there a way to write into your code that it constantly checks to see if you're in a forever loop and then break you out?
Oh, that's a really good question. At the end of this course, we'll talk about something called the halting problem, which kind of relates to that, which is this question of can you analyze a program and tell if it's going to run forever or is it going to finish?
Isn't that kind of what Powergram does?
Valgrind doesn't really care if you're stuck in a loop or not. Valgrind just tells you if and when you exit, how you did with managing memory. This question of looking at a piece of code, some programs you look at and it's like, well, you say, well, I is less than 10 and you never increment I, that's going to run forever, right? We can do that. But the question of can you look at any program and tell if it's going to run forever or not, that's a harder question. And that's something called the halting problem. And that cuts down to the heart of computing and philosophy and all kinds of other things. And we'll go through that probably the last week of the course.
You're going to be on the final?
Yeah. All right, so that's the basic setup of mathematical induction, right? And again, the way to think of it is if you can prove a base case, and if you can prove that a proposition being true for n is also true for n plus 1, then you can say it's true in all cases. Okay, and this floor tiling business, right? We never sat down and tiled, a 1024 by 1024 room. We just showed that if you could do it for a quadrant, you can do it for the whole thing. Right? That's all we got to do. That together with a base case and mathematical induction lets us say this is true in all cases. I'm going to leave it at that. I was going to go on to mathematical version, but I'd rather you sit with that idea. Wednesday, we'll look at this in a more mathematical setting. We'll look at some propositions about integers, and then build from there.
You have time to find